So this course is about modeling an inverter-based resource using PSCAD. Actually, I will be starting from the very basics. So let's look at a very simple circuit that looks something like this. For example, we have a source here. This is, let's suppose, a grid, and I have a DC source here. Now, if I want to connect this DC source to the grid, what I could do is I could take an inverter here and connect the DC source to inverter. Now, by switching the inverter switching in some sequence, I could create a three-phase voltage here. This is very common. For example, I could use a three-phase inverter and I could easily create a three-phase voltage here. So I have a three-phase voltage here and I have a three-phase voltage here. What I could do here now is, let's connect these points here, both these points here, by a circuit that looks something like this. For example, this is a RX branch. Usually R is very small, but it is unavoidable because R is the resistance of this inductor. Let's look at this circuit a little more closely. For example, let's assume that my VG has some for example magnitude, this VG, and its phase is 0. Let's remove this VG, let's put it here. Now if you look at it, by switching this inverter in certain sequence, the switching its controlling its switches in certain sequence, I could create a VC of voltage magnitude and phase however I want. For example, I could create a voltage here that is exactly in magnitude equal to this and also in phase with this. So I could create anything now here. Let's assume that I create some voltage here which has magnitude a little bit lower than this, or maybe a little bit higher than this, and its phase is a little bit different than this. For example, let's say it is leading a little bit. Let's assume VC is a little bit higher in magnitude than VG, because in the previous case the diagram get cluttered, so it's not very visible. Now the voltage across this branch is VC minus VG, and on phasor diagram it looks something like this. This is VC minus VG. Now let's assume that R is very small. It's usually very small. So if R is very small, then the current in this branch is almost lagging with respect to this voltage. So current is somewhere like here. This is 90-degree lagging. So IG is like here. Now let's keep it here. So this is my IG. I just brought this phasor diagram from here to here, so it's nothing special. Now if you look at it, the power dispatched by this into the grid is VC IG cos of the angle between them. And what is the cause of the angle between them? So this is the cause of the angle between them. And if you look at it, by changing the magnitude and the phase of this VC, I can change the power transfer to this grid. And similar is the case for reactive power. So let's look at few equations, and these equations are easily derivable from this circuit. So if you look at it, VC VG, sine of the angle between them, and divided by X. So these are almost the same equation but in different form. So if I change the magnitude or the phase of that VC, I can control the real power, and similarly I can control the reactive power by changing the magnitude. By changing the magnitude, it has a larger effect on the reactive power and smaller effect on the active power. So you could see that I could exchange active reactive power with the grid using an IBR, and that's actually that's the very basics of IBR, and obviously I will be explaining all this. And let's go a little further, and that how we can exchange active reactive power with the grid. So for example, if I want to exchange active reactive power with the grid, I need to know the magnitude of this voltage and the phase of this voltage, because if I don't know the magnitude and the phase of this voltage, then how can I create the magnitude here, and obviously I would know how should I control my phase here to exchange power with the grid. So there are so obviously we need some kind of feedback from the grid to the this is very important to deal with this coupling as well. For example, if I change VD, my ID changes, but when ID changes, my IQ also changes. So we will be talking about this, how you can independently control VD and ID, because if you change VD, your ID also changes. And if you look at your power equations in DQ frame, then power equations in DQ frame depends upon ID and IQ. So if you want to change ID, your IQ will also change, and if you want to change IQ, your ID will also change, and by that your real reactive power will not be independently controlled. So if you want to control real power only, your reactive power will be controlled as well, and that's not what I want. I want this system to behave as a synchronous machine. For example, in synchronous machine, if I want to change real power, what we do is we increase power to the prime mover. I mean, we open valve gates or anything. And if I want to control the reactive power of a synchronous machine, then what I do is I change the excitation of that machine. So in synchronous machine, we have very well defined independent P and Q control, but in inverter-based resource, it's not that straightforward. So by very clever manipulation of some things, some equations, you could and clever use of some techniques, decoupling techniques, you could easily get an independent real and reactive power control. So we will be talking about this. Of course, I have explained all of these through equations and everything, and after talking about the basics of IBR, actually it's not the very basics, it's quite complicated. After that, we will be modeling all of this in our PSCAD. So we will be looking at how PLL, actually that this is now a little bit advanced, so this is just an introductory video, so I do not want to get into this because I don't think anyone would get it. After that, we will be looking at the inverter itself, how inverter, what is the behavior of inverter, and how it introduces complexity into our design, and how to deal with that. For example, a total harmonic distortion, it introduces into a system which is very critical. So we will be looking at that as well, and for that we will be looking at some filter. What can we do to minimize the harmonics? And there are three common types of filter. So we will be looking at the pros and cons of every filter, and of course there is a example how to design a filter for some system. Actually, we will be designing proper IBR that would have a rating of about 250 kVA, and we will be looking at how we can design its inverter and that's its LCL filter. After that, we will be looking at how we can we will be looking at how we can design the PI controller itself, which will be controlling our system. So actually that's quite interesting. At for example, these controllers, we will be looking at these controllers, and I will be also talking about this, how this decoupling is achieved. For example, if you look at it, there is coupling. This part is from the previous diagram, this one. So to remove this coupling, what I did here is I just inserted an inverse of this here. For example, if you look at it, this one was ID multiplied by this and added to this. So what I did here is ID multiplied by this and I subtracted here. So for example, sorry, it was subtracted here and added here. So these were cancelled. And if you simplify this, then what you get is you get independent loops. For example, this loop, this is cancelled with this, so you get independent loops, this one and this one. So that's how you get independent control of real and reactive power. Actually, we will be looking at it at this. Actually, why ID and IQ, why P real and reactive power depend on ID and Q. I think I have explained it here. Yeah. So yes, I have explained it here. And where is the reactive power? Yes, this one. If you look at it, P depends only on ID if you do decoupling, if you perform decoupling, and Q depends on IQ. So this is very important, and we will be looking at it, all these equations. I will be explaining everything. Actually, it's quite lengthy, so I think this will take about 8 to 10 hours, maybe a little more than that. Actually, it's quite lengthy. And of course, lastly, for example, my DC, I consider my DC source a constant DC source. It's not usually the case. For example, PV cell is not a constant DC source, so we will be looking at that as well. And of course, for that we won't have, for example, let's look at it. I have let's look at this. Let's look at PSCAD, all the cases that I have. Actually, we will be making these cases from the scratch, so that you guys understand everything. So this is my DC source, which is not a constant DC source. So I have connected it to a buck boost converter. For example, it can change, it can increase and decrease. So buck boost converter will try to regulate it to a certain voltage here needed for. So this whole arrangement will be discussed, how buck boost converter comes into play, and what's the purpose of DC link, and of course inverter, and then LCL filter, and then step up transformer connected to the grid. So we will be looking at this whole circuit. Actually, I will be doing this step by step. For example, at first I will be only looking at inverter connected to the grid without transformer, directly through L filter. For example, something like this. Something like this. So this is an inverter. Actually, it doesn't look like an inverter, but it serves the purpose of an inverter. For example, I have three sources which are control sources. So VA is actually the output of the park transformation, which I used to calculate the reference value of VA, VB, VC. So as I explained earlier that I need PI controller and this decoupling loop, and then the whatever I get here, I reconvert it into a three-phase signal through inverse spark transformation. So I apply it directly to the three-phase sources. So we get a three-phase controlled voltage here. I can change the reactive, I can change the magnitude of these voltages and the phase of these voltages, and that's what we do using an inverter. So this is actually why I wanted to do this, because this is very simple to understand. There is no inverter, no nothing, just simple understanding how IBR works. I mean how I can exchange power with the grid if I have a control source, just like in synchronous machine. For example, in synchronous machine I have a control source. I can control the voltage and the magnitude of that synchronous machine. So it's similar case here, and we will be developing this slowly and slowly. So this is the full developed case. For example, if I could show you, this is this one. So this is a second case which I have removed the DC the source, the three-phase source, three-phase control source, and I have inserted an inverter. It's the same case, but I have just inserted an inverter, and I will be looking at this, what kind of harmonics we get and everything. So we will be developing our IBR slowly, step by step. After that, I introduce a DC source that is not constant. For example, let's look at it. For example, here. So here, when our DC source is not constant, then I need a buck boost converter. And obviously I have also introduced LCL filter. I think I have LCL filter here. So this is the same circuit with constant DC source, inverter, and LCL filter. So we will be designing this LCL filter. These values are not random. These are selected based on very specific performance of the LCL filter. So we will be looking at this inverter without this LCL filter and what kind of harmonics I get, and we will be improving that harmonics. For example, I think I was getting about 35% THD, total harmonic distortion, without this LCL filter, with simple, with this one. So 35 is quite high. So with this, I think I was getting about 1%, maybe less than 1% THD. So we will be looking at this, and also we will be looking at these PI controllers and how how KP and TI, time constant of these are designed. We will be looking at this. So actually this was just an introductory lecture, and of course it's quite interesting, and hopefully I'll meet you in the next video.